RL circuits. 1. The figure shows a circuit consisting of a battery E, an inductor L, a resistor R, and a switch S. You can see the switch here, kind of on the right side. Points 1 and 2 are also indicated, and we want to circle the answers here. When the switch is thrown to point 1, current will flow around the leftmost loop of the circuit in which direction? So when we flip this switch right over here, this battery will say that we're going to have current that flows in the counterclockwise direction. And when that switch is thrown, there would be an EMF induced in the inductor that is directed which way? Now remember, inductors want to oppose any change in current. And at first, before we flip the switch, there was no current. Well, as soon as we do, now there's going to be a current, you see my marker, coming down this way through the inductor. Inductors, remember, don't want change. So they're going to try and fight that change by having their EMF directed that way. When the switch is thrown to point 1, the initial magnitude of the current around the leftmost loop would be 0. We mentioned in a previous video that at the first instant of connection, an inductor acts like an insulator. When we flip the switch, at the first instant, there won't be any current in that leftmost portion of the circuit. A long time after the switch touches point 1, the current's magnitude around the leftmost loop will be E over R. A long time later, this inductor is going to just act like a wire. Once the current isn't changing anymore, it's as if we just have a wire there. Now the switch is flipped to point 2. When the switch is thrown to point 2, current flows around the outermost loop of the circuit in which direction? Let's go back for a second. When we had this on point 1, we were having a counterclockwise loop of current going around this left side, which means that the current was traveling through this inductor in this direction. And when we flip the switch now over to point 2, the inductor wants to keep whatever current there is happening. It's going to essentially release some of the energy that is stored in the magnetic field within its coils to keep that current going in that direction, which means now that counterclockwise current is going to be going around the entire outside of the circuit. We're going to skip the battery now. And when that switch is at point 2, what's the initial magnitude of the current of the outermost loop? Well, remember, an inductor will attempt to maintain whatever current it has. And for an instant, it will be able to maintain that current that was going through when we had it at point 1 for a very long time. In other words, the inductor, when we flip it to point 2, it's going to wake up and release some of its energy, and for an instant, it will be able to maintain that current that it had in it. How about letter G? When the switch is thrown to point 2, there would be an EMF induced in the inductor. We just talked about this, in that direction, because remember, inductors don't like change in current, and the current was going towards the bottom of the page, and then we flip the switch over to point 2. This inductor is going to wake up and try and keep moving that current in that direction. A long time after the switch has been thrown, the magnitude of the current will be 0, right? There's only a finite amount of energy that is stored in this inductor, and so that current that is going counterclockwise around here, it's going to eventually end up at 0. Speaking of that energy, the equation for the potential energy stored in an inductor L that's carrying a current I looks like this: 1/2 L I squared. You can see that the current has a large effect on how much energy is stored in the inductor. The greater the current that's going through the inductor, the greater the energy that is stored in the magnetic field in that inductor's loops, and which is then able to be released if the current starts to suddenly drop off. And there are several other equations, aren't there, in physics that kind of have this same pattern. Kinetic energy has that same 1/2 pattern. The energy stored in a capacitor. There are a couple of variables you could use for that, but there's a formulation. The elastic potential energy stored in a linear spring. Nothing super special about that last answer, but it's just kind of interesting.